All right. Without any further ado, let's talk about degradable mulching films and what this project is all about. We're in the second year of the project. So we started in 2020, and actually it was the middle of the pandemic, so we had a little bit of a delay start, but things are looking up now, and we're going to share some of that progress. So agricultural mulch films, AFMs, has been the acronym that we adopted. They are widely used to prevent moisture loss, to weed control. However, despite the benefits, there are some problems with disposal that is costly and adds to plastic pollution. After harvest, the growers need to leave, remove, dispose the conventional AMFs. And some of the two methods are incineration and landfill. And as I said, there is labor involved in this, and nowadays the labor and finding labor is becoming more of a concern. So there are commercial available films that degrade in place. So these biodegradable films, the idea is that you can lay them down and just leave them there, and they will disappear next year. That's a great promise. However, growers are reluctant to use these commercially available biodegradable mulch films, basically for two things. We've found out limitations in the mechanical performance, and as we found out in this study, I think some limitations in the format of those biodegradable films, and then the composition, the promise of the composition is not as the label said. A lot of times it starts breaking down, but not fully decomposed, and it's in the soil. So there is, especially in the US, a lot of reluctancy to adopt biodegradable mulch films. So when we set out to do this project, the objective was really improve the situation for growers by developing technologies that meet growers' requirement for agricultural mulch films that decompose in place. So how can we really improve both performance and biodegradability, and also apply known environmentally friendly technologies to the disposal of agricultural mulch films after removal? So if we cannot really develop a degrading place, what is an alternative that is environmentally friendly? And we specifically are talking here about using pyrolysis as an end-of-life scenario for not only mulch films, but a commingle mulch films and waste biomass, and work with growers to demonstrate the efficacy of the developed technologies and promote the adoption of degradable films on the film. So for the year one and year two, the main tasks that we set out to do include the benchmark of existing agricultural mulch films, and then the development of these technologies to degrade in place. We call it trigger mechanisms. How can we design interventions that will kickstart an accelerated degradation for these films that stay in place, that degrade in place? And also another task which we set out to do is, can we design our own film, a novel biodegradable mulch film that will meet performance and accelerated degradation requirements? In the alternative routes, we have the apply environmentally friendly disposal technologies, thermochemical convention, and we're going to give you a quick update on this. So let's look briefly what we do in terms of benchmarking. We procure a bunch of materials, resins, and also commercially available biodegradable films. In this case, we have LDPE for lab control, a commercial agricultural mold films. We don't know exactly what is in there, but we know it's mostly LDPE. And then some of the brands that are out there: EcoPlanet, BioBag, Bio360, EcoBio, Film Organic. This BioBag actually is not intended for, it's a biodegradable option in the market as a substrate, but it's designed more for shopping bags. And let me point out here the width of some of those films. A lot of, like all of the biodegradable ones that we found, they come in a smaller format than the conventional ones that are 5, 6, 7 feet, and that we realize could present some problems. We did some biodegradable or soil degradability experiments in the lab, and we found out, like, I'll show you in the next slide, EcoPlanet had a very minimal degradation, and then these ones we test them, found evidence of degradation. In the case of this Film Organic, this actually came late to the game. It's a local wholesaler of agricultural supplies. They have it there, so we're testing it as well, and we're getting some of that data. Let me show you this slide here. When we started this, we just put films in soil and expecting that they are gonna degrade, but even after 180 days, like, the weight loss of those films was almost not there. So that's the first, that was our introduction to degradable mulch films. If we see here, the blue is cellulose control. The cellulose control is showing us, yeah, there is activity in the soil. It can degrade cellulose. So this is a problem, and this kind of correlates with some of the problems that, hey, these films might not actually really biodegrade in the time frame that we need to. One of the things that we found out quickly is that the pristine films, they don't have any weathering, or they haven't been exposed to light, wind, rain as a traditional film will. So we developed a protocol to do a weather sample and then biodegrade it. We start seeing here some of the decrease in weight loss. For one of them, around 60% after 200 days, and then this one on top is the EcoPlanet that was showing, that wasn't showing a lot of degradation. So this was our introduction, trying to understand this field, understand what's happening, and with the follow-up presentations, we hope to address some of those questions. And the benchmark include the characterization for mechanical properties. We did tensile tests for films, and also some properties like tear resistance and impact that might be more correlated to characteristics that we look for on the film. And some of the learnings here. So, and let me introduce this. We did some preliminary trials. We actually talked to, and let me see if he's in the attendees here, with a local farm, Kirby Farms in Brockport, and they have been a great partner for this project, and they allow us to do some preliminary trials. So we started laying film on the film for this growing season, and started analyzing how these behave. And the objective here is to relate those benchmarks to the field performance, to gain experience prior to conducting trials for the developmental technologies. And we are scheduled to do field trials in year 2, in year 3, and year 4 of the project. And note that this benchmark plan was not originally envisioned in the original plan, but it has proven to be very informative and a big learning for us. So some key learnings: the roll width must match the grower's application process for a fair comparison. So the attachment to lay film has to be flexible, or we need to really provide film to the grower that fits that equipment. Otherwise, we run into some problems trying to feed a 4-feet roll into an instrument or an attachment that was meant for a bigger roll. The tensile strength and the cross-direction tear resistance proved to be critical for a critical fit for use property. And although biodegradable films had significantly lower cross-direction tear resistance than the conventional, some of them, they were still fully fit for use. So let me show you what that means. This is the same data that we had before, but here you can see sort of like in that, all that data, where can we focus on the tensile strength right here, and then the tear resistance. And what is the tear resistance means? Like, for instance, this film organic had a low tear resistance in the cross direction. What that meant is that any puncture or any crack will result in a full crack propagation, and it will stop completely the lane mulch process, and it has to be restarted. However, the team was able to kind of find ways around and lay some of these films, including the film organic here. And this, and we can see also that these films have considerably good tensile stress. Now, in terms of the study of triggers and the development of novel films, we have initiated this mostly at the lab level, and the idea is to get our best approaches to scale up and test it on the field. We set out to do three technologies. One we call microbial activation, one surface activation, and one development of a novel film. In the microbial activation, Harshal is going to present on that. We have some evidence of the increased microbial growth on film materials, and there is some interesting stuff happening here. Stay tuned. In the surface activation, we propose the use of plasma, and we have that evidence that of the ability to enhance biodegradation. And we're also trying to produce novel films. In this case, we see this photo here. We want a thick starch core layer, and then polyester thin layers on top. And Ivan is gonna give us some information on that. On the pyrolysis side, and Tom Treble is here with us. Let me ask Tom, do you have your presentation in the background?
Yes, Carlos, I do.
All right, let me just give, I just put a one here very quickly. So the pyrolysis study, this is an alternative route, and it's very interesting, and to test those known technologies that can give us an alternative organic waste, and in this case, commingle with films end of life. So woody biomass and LDPE can be commingled in the pyrolysis process. The presence of LDPE does not degrade the biochar quality, and it appears to be a small fraction. It appears that the small fraction of LDPE actually could enhance pore formation. But let me stop here for a second and let Tom give us a quick update on that. We had a master's students doing this work, and we presented actually this work already in some conferences.
So Carlos, should I switch over to my?
Yep,
okay.
You can share your screen.
Okay. Yeah, so just a very brief update here to follow Carlos's introduction. This was work that was done initially by a Master of Science student on this project, Ibrahim Sise, who's now working at American Sugar Refinery. And since Ibrahim left campus, our PhD student, Ivan Hernandez Charpak, has done some additional analysis, which is what I would like to just update the group on here very briefly. Just for background, we considered 4 different types of agricultural wastes in this part of the work, and those included wooden pallets, crop residues, cardboard, and woody biomass. Wooden pallets are listed twice, but the 4th material is woody biomass, which is represented by these wood pellets here that are for a wood pellet stove. So as Carlos mentioned, copyrolysis is being looked at as an alternative to, the ultimate objective of this project is to develop new biodegradable agricultural mulch films. But as a second objective, which is maybe somewhat lower risk, would be the copyrolysis option, which may not be as attractive as the main objective of developing new materials, but is an approach that we think would be substantially more sustainable and more environmentally friendly than the current practice of either incinerating or landfilling these materials. So we looked at pyrolyzing these materials in combination with the low density polyethylene mulch film to understand the properties of the biochar that materials that were thus derived, and could those materials indeed be used as an additive to the soil. And as the literature clearly demonstrates, biochar enhances soil organic carbon content and enhances microbial activity. We took a lot of data to characterize these materials, thanks to Ivan. He provided a lot of data, but just to highlight what we found, and these are scanning electron microscope images of the biochar made with a combination of wood pellets and low density polyethylene at 3 different mass ratios. So the top row of images corresponds to the pure woody biomass produced at 500, 650, and 800 degrees centigrade. And then as we move down, we have biochar produced with 95% biomass, 5% LDPE, and then finally 75% biomass and 25% LDPE. And what we found consistently is that higher temperature creates a higher surface area and a higher density of micropores. But this data, in combination with a number of other measurements that Ivan took, indicate that the presence of the low density polyethylene has very little impact on the properties of the biochar. In fact, what we found is the presence of the plastic phase actually enhances the formation of micropores in the biochar, which is illustrated in the center of the figure on the right. And this implies that biochar will actually have a higher water carrying capacity and may also enhance the ability to support the microbial community in the soil. And this is actually consistent with literature that's results that have been published in the literature showing that small amounts of plastic combined with biomass actually produces biochar of higher quality. So that would be our high level conclusion. Co-pyrolizing small amounts of agricultural mulch film material with biomass produces biochar of high quality, and there's evidence that it may actually be higher quality for some applications.
All right, thank you, Tom. There is a quick question here, just as a understanding pyrolysis. Burning of materials at very high temperatures. And
Okay. So yeah, I apologize for that. Let me just define pyrolysis as it's not burning because we're not adding oxygen. This is thermochemical processing at high temperature, so 500 to 800 degrees C, in the absence of oxygen. So the material doesn't burn, but it does produce a number of co-products, one of which that we're focusing on is biochar, which is carbonaceous material that's very stable and recalcitrant. And so pyrolysis reaction will concentrate the carbon into the solid phase, as opposed to incineration or burning that would convert that carbon into CO2, which would go off in the gas phase. So pyrolysis is distinctly different from burning or incineration.
All right. Thank you, Tom. If
Okay.
anybody has a question, I think you can raise your hand or write your question in the chat, or yeah, so we can shout them out loud here.
Okay.
Thank you, Tom.
Okay. I'll
So
stop sharing then.
yeah, next with us is going to be Ivan Hernandez. So Ivan, the floor is yours.
All right, thank you, Professor. So let me share my screen. So hi, everybody. My name is Ivan Hernandez, and I'm gonna talk to you about these on-field trials that the professor mentioned, dive a little bit more on that. And but also gonna talk about the prototypes. Here you see a clip of one of those exciting prototypes we're able to make. And we will also, like, as we were saying on the on-field trials, talk a little bit about those results of the on-field trial and how we see differences in properties of the late plastics, like DSC, that I will explain what it is in a little while. So first, a little bit the structure of my presentation so we don't get lost. I'm going to talk on why and what we expected on those trials and what did we get. Then I'm going to talk a little bit about the starch core that the professor mentioned. And finally, I'm going to talk about the prototypes we made. So as you see, on the on-field degradation, we went on May with Harshal and worked really, really hard on laying some plastics, 3 different plastics, Film Organic, Bio360, and EcoBio. And we laid them because we knew that when we, just in the laying process, it changes the properties of the plastic. You see the wheels there in that picture show that there is tension already applied to the plastic. And so maybe the degradation process is going to be different than an untensioned sample. So we wanted to understand a little bit more the behavior of the plastics on the field. And because the main degradation indicator literature usually uses is weight change, and that is sometimes hard to get in from the field. So we wanted to also explore what other indicators we could get for degradability. So we went there in May and we took samples every month. We also monitored temperature and relative humidity. And what we got, well, we did first some mechanical testing. And so that mechanical testing gives us a lot of information. One is the elastic modulus. The elastic modulus, we can think of it like it's like the stiffness of the plastic. And we see there is a clear trend that it becomes more stiff with time. And that is nice in the sense that it corroborates what we've seen in literature. And it's also continuous measurement that maybe gives us an indicator. The more stiff, the more degraded. The problem with this as an indicator for biodegradability is that not all the samples were able to give us an elastic modulus, and not always, it was not always possible to get that. And even if we got, sometimes the error bar is huge, like in the last point of the Bio360 in the cross direction, it was really hard to determine. So that for elastic modulus. Then another key property that the professor mentioned was tear resistance. And tear resistance is very important when laying the material. But once it's laid, as you see, all the plastics lost tear resistance after 2 months. That is okay because they don't need it anymore. It's just important when laying the plastic. But for our purpose of indicator, and it's not the best because after the 2nd month, all the plastics have very similar tear resistance, and that does not give us an idea of who is degrading more and why. But for the performance, it's good to know that after 2 months, all plastics lose tear resistance, and that's okay. Finally, we also get from mechanical testing the tensile strength. That is a continuous measurement. We can get it all the time, and there's a clear trend of going downwards to lower values from the initial tensile strength of the material. So that can be maybe used as a good indicator for biodegradability. But we not only did mechanical testing, we also did some thermal testing. So that one I was talking about, the differential scanning calorimeter, allows us to have an insight on the plastic structure. And here we compared the May samples just after we laid them to the October samples. And we do see some clear differences on the behavior of the plastic. So DSC may be a good way to differentiate degraded versus non-degraded samples. And another thing we did was thermogravimetrical analysis that shows us how the weight of the material changes with the ramping temperature and gives us an insight on the dynamic of the plastic. And sadly, we didn't see any major differences between samples of May and October. So it's not that sensitive to degradation as the DSC. So the on-field trials informed us on the behavior of commercial plastics on the field, and the sampling of those plastics showed us that DSC, elastic modulus, and tensile strength gives us information about the different degradation stages. Now let's talk about that starch core the professor was talking about. We wanted to process the plastic. We want to process it with the plastic, so it needs to be plasticized. Therefore, it needs to be thermoplastic starch. From there, we have either two ways. One, we can mix it with a low molecular weight polymer, or we can plasticize it with either water or glycerol. We chose water as plasticizer. Why? Because we know it increases also the microbial activity. But after meeting with industry and looking through literature, it's not very clear how water and mechanical properties of starch behave. So therefore, we prepared some samples at different concentrations of water in a small mixing head and a compression molding. And we found out that 45% water did a good balance between the water content and the mechanical properties. The problem is that this produces very small amounts of the thermoplastic starch. And if we want to do a film, a lab scale film prototype, we need pounds, we need kilograms. So I had to find another way to make this work. So the way I made it is first we dried the starch, and then we mix it with water and a little bit of glycerol for 10 minutes. Then we put it through a meat grinder, and then I put it in an oven for 15 minutes. And I repeat this twice. And after the third time, I can put it in a single screw extruder with a temperature profile that goes from 200 Fahrenheit to 275. 200, especially, it's important at the exit, so it doesn't bubble and we don't lose extra moisture. In the oven, I have to mention, it's covered, and so we don't lose moisture. And after the extrusion, we can pelletize it and use it we were able to produce pounds, even kilograms of the material, and get it ready for the prototype making. But further testing, here you see a TGA of 2 different samples, and further testing showed us that we didn't have that 45% moisture. Why we know that? Well, TGA gives us how the material behaves with temperature, right? And between around 100 Celsius, we should see the drop because of the content of moisture. And we see that we don't have a 45% drop. We have between 20 and 8, and the actual average of samples was 12%. So even if we inputted 45% of water, the actual moisture content is unknown, is around 12. And this loss of control is because even if I was careful and tried to not lose moisture, I lost it due to these temperatures that are very close to the boiling point. But why is this showing? The film, now I'm going to talk about the prototypes. And those prototypes, we did them in a lab field. Why is it showing like this? Sorry. I don't know why it's showing. and a blown film extruder. And the first prototype we made was with polycaprolactone. So the polyesters in the outside part was polycaprolactone. Why did we choose this polymer? Well, because the processing temperatures were very, very close to what were the processes of the starch, as you see here. But because of the picture, and it's you see that it's not homogeneous. It's very heterogeneous, and there's conglomerates of starch. Well, this is because it didn't flow right. The RPM in this table gives us an idea of how much starch we're inputting inside the plastic, and it shows only 4. And this is, we had to limit this. The constraint was the pressure that was getting to the limit of the machine, so we couldn't get any higher. Nevertheless, the performance was interesting. If you look at this video here, the mechanical tension is carried by the outer layers, and the starch inside just flows. But again, it's very heterogeneous, and the thickness ranged from 40 microns to 500. Then the second prototype we made was with PBAT. We were a little bit reluctant to use PBAT because the processing temperatures are much higher, are like 120 Fahrenheit higher. And we were scared that it was going to burn our starch. But we were able to produce a very homogeneous, actually, prototype. And the speeds that we were inputting starch were very, very much higher. So it was producing a very homogeneous sample that also, as you see now in video that appeared very savagely, it also performs very correctly. The outer layers carry the whole mechanical tension, and the starch flows inside. The thickness range was a little bit bigger than what we expected, but way more homogeneous. So that was great. And now, so finally, we achieved 2 different lab scale prototypes that we need now to test for biodegradability better. What are the next steps? Well, for the film manufacturer, we have to tune and refine the process to find the thicknesses of each layer we want, and to understand a little bit more like the complexities we find there. Well, the way a blown film line works is that the plastic comes like this, and then it roller casts, and the inner layers touch themselves, and we were finding that they're sticking to each other. So the PBAT is actually sticking to each other, to itself, and fusing in only one layer. And so this explains why we're having such a thickness. If you look at the picture, we have a middle layer of PBAT in the middle. So the thickness should actually be half of what we got. And we have to then maybe add an anti-blocking agent so into the inner layer of PBAT, so that doesn't happen. And also we have to upscale the width of the film. As the professor was saying, width is an important parameter that we are a little bit low, and we have to get it bigger. Then for the degradation indexes, that we have to find a way to connect DSC, elastic modulus, tensile strength, to be able to determine a metric to be able to assess degradation of a plastic film on field. And finally, for our starch characterization, well, we have to find a better way to control moisture in the manufacturing process, so we can have more control on the percentage of water. That is where we are in our advances in this site. And thank you. If you have any questions, I would be very happy to answer.
All right, thank you, Ivan. I'm monitoring here the chat. And Anne asked a question about pyrolysis. And do you want to discuss that further, or?
On the pyrolysis, let me see the question.
Yeah.
Have we found? Oh, but Professor.
Yeah, I responded to
Yeah,
Anne.
Okay. Yeah.
Carlos.
Yeah, and if you want a further discussion, let us know. And
Yeah, I was just wondering about the long-term impact of the low levels of LDPE in the char from a bioaccumulation in the soil. I didn't see a response. I'm sorry if someone sent one.
okay, yeah,
Yeah.
the response. Let me read the response. Or no, go ahead, Tom. Let me.
Yeah, so and I did respond in the chat, but what I said is that the pyrolyzed LDPE biomass samples that were converted into biochar were shown to be essentially the same as biochar produced from biomass only. So because of that, we would not expect any bioaccumulation issues in the soil with these materials. You know, again, bearing in mind that we're processing only small fractions of LDPE with mostly biomass, and those mass fractions are based on the actual masses of wastes that are produced in, data that was provided by our partners on this project that run several local farms.
Okay, no,
And-
that's,
And Tom, would it be fair to say that a lot of the polyethylene will be in the gas phase?
Yep. So
Yeah.
exactly. So based on the analysis that we've done, Anne, on a pretty extensive analysis on a wide variety of samples, because the biochar doesn't show any different properties when we add LDPE, the expectation is that the components of the LDPE come off in the gas phase during the pyrolysis reaction.
yeah, and that probably is that off-gassing is what creates the cell structure, perhaps.
Correct. Those
Correct.
secondary pores that we showed in the SEM images are a
Yeah.
result of the gas phase products from the reaction.
Yeah. Okay, thank you.
You're welcome.
We have another question from Jarmila saying, I'm going to read.
Okay.
She asked if that she thinks that the tearing function is also important during the plastic operation because it could allow further tear and introduction of the weeds. That is one of the main functions of the plastic laying. And what we found out is that the thing with the tear force is that that is when we applied additional tension, so additional force to that. So if the tear resistance does drop a lot, and but there is not going to be like additional tension that's going to be made during after the laying. It's not going to be comparable to the one that was during the laying. So you're totally right, because the idea is not to have additional gaps where the weeds are going to grow, but if the tear resistance falls, it's not going to be open further. So there is no worry on that side.
And you guys saw the films after, like let's say the October ones. Was there holes or something based on weeds or not really? That didn't.
Weeds sometimes make their way through plastic. Yeah,
Okay.
they were open to open it and be like, yeah, we can do it. But that was it was not like major tears.
Sounds good. All right, let me give the floor now to Harshal. He's going to talk about this microbial activation and what the work we've done in that area.
Hi, Professor, can I be heard?
Yeah, I hear you loud and clear.
Okay, perfect. Hi, so I'll be talking a little about agriculture, accelerated biodegradation of agricultural mulch limbs in soil and compost environments. Shout out to my co-advisor, Professor Jeff Lodge. Professor Carlos already mentioned a little about microbial trigger, and I wanted to explain a little bit in detail what the microbial trigger mechanism means. The concept when the grant was applied for was, can we isolate microbes directly from the ag soils, which specifically degrade bioplastics, and use them as a spray at the end of the season once the harvest is over, which will accelerate the biodegradation of plastics. And then can we till the plastics into the field so that the ideal scenario would be that over the winter, the microbes would break the plastic down into the soil itself, and you would not have plastic left after winter or after spring for the next laying season or next growing season. And we started to work on that particular idea or concept. So we started with acquiring commercial mulch films. We acquired two biodegradable mulch films. One of them has a polymer known as Bio 360. It's nothing but it consists of other copolymers, which are thermoplastic starch, polycaprolactone, and PVAT, which Shivan talked about a little. The second one was obtained from Organic Solutions, and the base polymer is EcoVio, which contains these two polymers, which is polylactic acid, small mistake here, and PVAT. And we used low density polyethylene based film as control, as shown here. This is the low density polyethylene based film. And we used another cellulose based film as a positive control, as cellulose does tend to degrade well in soil. And we wanted to have something to show that the soil is actually active and not have to worry about whether the soil has microbial activity or not. And these are the two 4x4,000 feet rolls. This is the Bio 360 and this is the EcoVio. EcoVio is a black and white film, and Bio 360 is an all black film. And then we looked at soils. Initially, we thought maybe we can use actual ag soils from fields, but because of seasonality and changes, the microbial communities change, and we decided to go with a store-bought soil. And we chose a Boang compost and manure mix. We decided to choose this first because it contains a huge or large quantities of microbes and very diverse quantities of microbes, types of microbes. This shows a potato dextrose agar plate with antibiotics and restricts the growth of bacteria. So all of these are all fungi colonies, and you can see many different types of fungi growing at 25 Celsius. And these are 10 to the -4 dilutions. This also shows that there's huge quantities of microbes. Same thing for the bacterial colonies. We were able to isolate 5 from 10 to the -4 to 10 to the -8 dilution. And you can see different types of bacterial cultures and colonies. Finally, we wanted to also use this particular soil, as it had manure and compost, for actual composting of our plastics. And I decided to run a potato dextrose agar plate, which is the fungal plates, and look at if whether microbes, whether fungi grow at 40 degrees Celsius or not. And we are able to get different types of microbes as compared to this particular 25-degree incubation. So we were able to use this particular type of soil for composting too. So we started initially with burying our samples, and by burying I mean we cut this the plastic film samples in the sizes 3 by 3 inches, and we buried them in soil bins as shown. And at regular time intervals, we took these out, and over time, as we saw some biodegradation, we were able to take weight loss as a direct measure for biodegradation. And based on this, we were able to isolate specific microbes. The isolation of microbes was done 2 ways. One was using a sterile swab directly on top of the film. So we would swab the film exactly on the top and isolate the microbes directly from the film. And second was to actually use the soil just around the film and serially dilute it to get 10 to the -6 dilutions. This is just a sample plate of what we got using soil, and similar would be what we get using the sterile swab. So the plates on the top here show fungal cultures, and you can see different types and varieties of fungi growing as you would expect. And again, these are bacterial cultures at the bottom, and you can see different types and varieties of bacteria growing. Now, the problem we ran into is how do you know which of these cultures of bacteria or fungi biodegrade the films, and which of them are just hanging because the surface is solid and there is something to sit or stay on. And we decided to go back to the literature and came up with another method. We call it the culture refining method. Here we used a powder of the plastic instead of the whole plastics. And the method has 3 main components: using a mineral media, which is nothing but a salt media. It does not have any carbon source. And mineral media we chose is the Bushnell-Haas mineral media. It was originally used for studying biodegradation of hydrocarbons, and we thought that might be a perfect media to test our films. And again, we cryo-grinded the mulch films into microplastic powder, thus increasing the surface area and reducing the size massively. And finally, we use this the soil, which I talked about, as an inoculum to isolate the microbes which we wanted. And a little on the culture refining method and the process itself. We started with the whole film. Then we grinded it up to a very, very fine microplastic powder. We used the soil as an inoculum, and we grew these up in actual Erlenmeyer or shake flasks. We bled the soil out for carbon and nutrients. So we put the soil into a saline solution and incubated for 7 days, at which most of the carbon and nutrients would have run out. And then we used that soil and inoculated a fresh shake flask with this particular powder and this particular media, which is the Bushnell-Haas mineral media in a specific ratio. And a small inoculum from the soil flasks went into individual plastic shake flasks. After 20 days, we re-inoculated from the old shake flasks into a new set of shake flasks with fresh media and fresh powder, and we repeated this 3 times in total, just to eliminate any cultures which weren't growing, and also to enhance the cultures which were growing. Finally, after about 3 months or so, when we had our refined cultures ready, we incubated these powdered plastic Bushnell-Haas media agar plates, and these are nothing but the same mineral media in an agar form, with the plastic powder sprinkled on the top. And we incubated these in duplicates for 7 days and 14 days, after which we isolate the cultures on a more generic media plate, which is the plate count agar, and refine our cultures. And here we have some mixed cultures as shown. The question we asked was, okay, how do we know if this method worked or not? And we have a very specific set of microbes which break down these plastic. So we wanted to generate a growth curve based on these microbes. So we incubated these microbes in a generic media. We use the triptych soy broth medium, where it's good to grow culturable bacteria. And we grew these in shake flasks like these, as shown. And we transferred these to centrifuge tubes and centrifuged the cells. So we had the packed cells and the supernatant. We threw out the supernatant. We added some Bushnell-Haas media, which is the media which we originally used, which is nothing but a salt solution. And we again mixed the cells back up in the Bushnell-Haas media. And this we did this just to clean the cells up of any polysaccharides or any other nutrients stuck to the cells. We did this 2 or 3 times, so recentrifuging, cleaning, and recentrifuging, just to remove any nutrients or anything else. Finally, using the isolated and suspended cells, we re-inoculated our fresh Bushnell-Haas mineral media powder and powder mix. And at T0, we plated these. And we wanted to do a growth curve. The issue with doing a growth curve with these plastic powders inside these media is you cannot do a simple growth curve. A simple growth curve is nothing but actually cell density. So as bacterial cultures grow, the media becomes more opaque, and you can measure that using optical density, and then drop in optical density or increase in optical density. But we came up with another solution. We used these PCA plates, which I talked about, these refined plates, and we incubated, serially transferred these to 10 to the negative 5th, 6th, and 7th dilutions. And we did a log of cell count versus per ml versus time. So it went something like this. At t equals 0, we had certain number of colonies on this particular plate, which is the plate count agar. And we calculated a log of those number of cells. And then in next equals 5 days, 10 days, 15 days, and 20 days, you took readings. And as you can see, the number of the cells go up, or the colonies go up. And again, the cell count goes up. And we were able to quantify that in a simple graph, which is the log of colony forming units per ml over versus time. And you can see there's a half to a 1 log increase in the number of in the growth of cultures. And this kind of gave us an idea that, yeah, I think the cultures are consuming these plastics. So we have isolated organisms which break down the plastics. Now, the next step was to actually identify what the cultures are. We at this point, we did not know the genuses and the species of the cultures. So we did a 16S rRNA sequencing, and these are the sequencing results for the the 4 plastics which we used, and LDP was the control. And as you can see, most or all of the majority of the cultures, the genuses are predominantly Agrobacter or Pseudomonas, and different species of these. And at first we were surprised that we got the same 2 bacteria for all of the plastic types. The plastic types vary quite a lot in chemical structure. But then we realized maybe because the refining process was so stringent, and it removed anything else which was not growing and only kept the organisms which were growing. And maybe that is why we got a very fixed set of cultures. And this is where we are so far. And in the future slides, I'll show what are the next steps based on these experiments. I'll be moving on to composting now. And we chose composting as a screening process. As Professor Carlos talked about, some of these films, when they are pristine or fresh, take a long time to biodegrade or don't show biodegradation or any signs of biodegradation till 180 or 200 days. And so we wanted to come up with a solution where if Ivan or if the next student is going to speak Swapnil, they give me their films to test. I'll be able to give them an answer back within 60 or 90 days saying that, oh, this particular film is doing well, or this particular method is working well in biodegradation versus this particular method is not working well. And so composting was a good way to accelerate the biodegradation of these, and the literature does support. Also, the films technically are chosen or certified compostable. And so we tried to come up with a reliable and consistent method for composting. So we started by using a test substrate, which is coffee grounds and coffee chaff, and did not start with mixed food waste compost. Reason we chose coffee grounds and chaff is because it is a very standard substrate. The nutrients don't change over time and space, so hence makes it very repeatable. This particular experiment, at least this first trial. And again, the inoculum which we chose is the Boang manure and compost mix that I talked about before. And the objective of the first trial was to compare forced airs versus naturally aired compost. So we had these 50-gallon bins, and we wanted to compost. We wanted to set up our composting these kind of 50-gallon bins. So we chose to force air through these through PVC pipes at the bottom, and forcing the air throughout the compost just to push more oxygen in. And we wanted to see if this makes a difference in the actual biodegradation versus just having a static pile sitting there. The second objective was to test these custom-made mesh bags. So the challenge with these kind of large composts was how do you keep your samples in the compost and not lose them, or not lose the order of the samples which you have kept, or because again we are measuring weight loss, so the order of the samples is very important. And we came up with these mesh bags where you can keep the triplicates of the samples in individual mesh bags and label the mesh bags and pull out the samples which you need at specific time points. And we weren't sure if this method would work, whether the microbes would microbial activity would hinder because of the mesh bags, and so on. And so then and the final objective was to develop a consistent and reliable method which was easily repeatable, and we would have consistent results. And some results which we got from our composting trial was, first, the mesh bags only slightly hindered microbial activity, and the second, cellulose biodegradation, which we generally use as benchmark, we saw that forced aired compost perform better. And these 2 points are seen here. So if the mesh bags would have to hinder the biodegradation of cellulose, we would have seen a much slower loss in weight of the cellulose, but we do see a quick weight loss in cellulose, similar to what we see in soil. And the forced-air compost which you use using air pumps showed a much better cellulose biodegradation rate as compared to a non-air compost as shown in this graph by the red and the blue lines respectively. And finally, at least we noticed in 60 to 90 days, couple of films having 5 to 7% reduction in weight. And this is just a scanning electron microscope image of 2 of the films. One of them one of the film, this one is a T0 sample, which nothing has, there's no biodegradation on, there's no surface change as seen here. And there's some amount of surface change as seen in this particular image after 90 days. And finally, based on the initial results, we plan to set the next set of experiments on composting. And I'll talk about that in the next few slides. The next steps for my set of experiments or biodegradation based experiments are, first, we already know what our cultures are. Now we want to see if these individual cultures break down individual biopolymers used in the original film manufacturing. For example, EcoVio contains these 2 biopolymers, which is PB80 and PLA. Now, the cultures which we isolated for this particular polymer, do they break down both of these plastic types? And that is the real question we want to ask, is if they break down both of these plastic types, then we can choose the one which is better for a microbial spray. So both of these cultures don't have to compete just to break the plastic down. Another important test is going to be CO2 evolution or testing so aerobic respiration or breakdown of these plastics is going to lead to water, CO2, and cell biomass being made. And it's very easy to test CO2, and we want to do that with our cultures just to see we can get a CO2 curve or a CO2 evolution curve. And finally, figure out a method to deploy these, like the microbial trigger, which Professor talked about. We need to find if whether these microbes can be grown on large scale, and again can be sprayed on, and the whole process can be tested out. And finally, setting up a large scale 50-gallon compost with running 2 or 3 different types of experiments in one bin, and actually optimizing or running these experiments efficiently, as it takes a long time to set up these large scale composts. Some other experiments we are looking at are based on the on-field weathered films, which Kirby Farms is helping us, which we set up in the Kirby Farms. We want to do a CO2 evolution test just to see if these biodegrade better than the pristine films, and that kind of proves the point that as these films are weaker in mechanical properties, bonds are easier to break. It may be that the evolution of CO2 is faster, or there's no lag phase, or we see a very little lag phase as compared to pristine films. We want to again use composting on these films just to get a more realistic data of what happens to real life or on-field films in an actual compost. And finally, using the microbial spray on these kind of films, which is going to be a more realistic experiment. Looking at weight loss and microbial activity over winter. So we set up November was the last day when the harvests are over, and then they take the last month where the harvests are over, and they take the films out in the field. And we took some of our films out, and we buried them in the soil in the mesh bags as shown before, and we kept them in the field, and we want to see if these will biodegrade over the winter, and do we see any microbial activity over the winter on these films in the actual ag field. And we want to look at anaerobic digestion. This is just a small scale lab setup for anaerobic digesters, and you want to see if these films can be broken down anaerobically, and also because anaerobic digestion, again, these sensors are very sensitive, we'll get a much better data of biodegradability and trends of biodegradability. Thanking their team, Professor Lewis and his student Swapnil, and they work on plasma treatment. Professor Carlos and his student Devan, they work on the multi-layered films, which Ivan talked about, and Professor Trebolt and his student, now graduated, Ibra, and they work on biochar making. Our partners at Cornell Cooperative Extension and Kirby Farms, and this is our webpage, and we've started to paste our publications and whatnot on the webpage now. Back to you, Professor. Any questions I can take?
Yeah, so take note, everybody. We just went live with this website. It's, I think, a week old. So www.rit.edu/sustainable agriculture. And you can find more updates on the project, and also list of conference and publications that have come out, and some of them are in process right now. We have a couple of papers under review. I think we have time for a quick question, and then we switch, but we can continue the discussion offline. Elizabeth, you had a question for Harshal, so I just
Sure, thanks.
and again, thank you, Elizabeth and Jarmila. They are here from Cornell Cooperative Extension, which is part of our core team, and has been really instrumental to make any progress. Go ahead.
Sure. So, Harshal, I'm really impressed with all the things you did to figure out what microbes are around and what might have possibilities, and also that you're looking at so many different ways to break down the material. I think that's really what we need. Is we need some solution to deal with the field plastic in some way. I don't have I struggled a little bit to follow all the microbiology of it. So my question is, the bacteria that you grew out, any fungus in there, and how much does the temperature that you raised them at have an impact on them? Asking because the field conditions that we're going to have during breakdown, say they're spraying something on the plastic late in the field season, it's early September, we're really looking at field soil that's probably no warmer than 60 degrees, more realistically sitting in the 40 to 50 range for a period of time. Is it likely that these bacteria are going to function well at that, or
so we try to again do all of these experiments at room temperatures, where the air is ambient, at 20 to 25 Celsius. So I assume they should be okay at 55 to 60. Again, we have to test this out. It may be these may work slower at lower temperatures, but if the plastic is still tilled into the soil, it may be that over at least during the day you would have slightly higher temperatures than ambient air, and so it may work better at least during the day, and go dormant during the evening where the temperatures are lower.
okay.
And as I said, I think this can be food for a very large discussion. And Elizabeth, we can schedule that with the group, and at least understand like those research questions that we need to look at.
Also, you talked about the fungi. So we did not select any fungi. Again, as you had mentioned in our one of the previous meetings, where a lot of growers do use fungicides, and so we were challenged by, do we actually test out fungi? Again, I am looking at one specific set of fungi, and this one is called Pleurotus ostreatus. Again, it's food grade, but challenges with fungi is that we tried a lot of different ways to test these on plastics, but as fungi need, bacteria can grow on very minimal salt solutions. Fungi need a little bit more refining. So I am trying to grow these up on the plastics, and trying to figure out one specific species of fungi, and if it works, then maybe we have something with the fungi. But I think overall, Professor and I thought just bacterial cultures may be a better solution than fungi.
No,
but again, we are looking at fungi too.
I agree. I think you're right that the fungicide exposure is much higher than copper exposure, and it's probably a good way to go. Thank you for answering the questions.
All right, thank you, Elizabeth. And then yeah, we need to meet sometime soon, and also start planning for 2022. Next, we're gonna hear from Swapnil talking about our energy activation. So let me do that.
Good afternoon, everyone. I'm Swapnil, and I am a grad student in mechanical engineering, and I'm working with Dr. Lewis and today I'll be presenting some of my research that we've been doing over the last 1 or 2 years. We're studying the effect of plasma treatment on commercially available mulch films. I have divided this presentation into the following parts. First, I'll talk about our plasma treatment method and why we are doing plasma treatment. Moving on, I'll talk about a bit of the film characterization that I've been doing before to compare how it performs before and after treatment. And then I'll present some degradation data in terms of soil burial trials and composting, and support them with CO2 evolution data as well. Finally, I'll talk about some of our future plans and next steps. Our goal for this project is to determine if plasma treatment enhances soil degradation of these mulch films. Plasma, for those of you who haven't worked with it before, is a stream of ionized gas. It contains electrons, ions, and free radicals. Plasma treatment is extremely popular in the modification of polymers in literature and in the industry. It has been commonly used to modify adhesion properties of polymers, and it's an environmentally clean, cheap process that allows for fast processing. Plasma treatment can introduce new functional groups on polymers. It could deposit new types of polymers on these films. It could also etch or increase the surface roughness of the films, and also sometimes it could result in cross-linking of the top surface. Biodegradable mulch films are commonly used in some farms, and it's extremely common in literature. Table 1 shows commonly used mulch films that I found in the literature, and something that's common in all of them is that they make use of PPAT, PLA, or starch in some form or the other. And these films are generally degraded by a degradation mechanism called microbial hydrolysis. For this work, we have mostly focused on a commonly found mulch film called Ecovio, and it's a blend of PPAT and PLA. We thought that it's a good representative of the most commonly occurring mulch films in literature. We make use of a Cortec PJ2 gliding arc plasma treater for our research, and the setup consists of our films as shown in figure 2a, wrapped around a cylinder which is placed 1/4 of an inch below the plasma head. The cylinder is rotating at 130 RPM, and the films are treated for 10, 15, and 20 seconds. We had to rotate the films because plasma treatments sometimes generally increase the surface temperature, and we didn't want these films to melt. That's why we wanted it to continuously rotate so that the films have the time to cool down. This figure shows one of our films getting treated with the plasma treater. Before I start presenting any of my data, I would like to talk about the naming convention that I followed in the following slides. How I've named the samples follows EV 1, 2, 3, 4, 5, where the first 2 letters correspond to the material name. Here EV is Ecovio. The next 2 digits correspond to the distance from the plasma head. Here 1, 2 would mean 1/2 inch from the plasma head. The next 2 digits correspond to the amount of time in seconds the film was exposed to plasma. Here, 3-4 would correspond to 34 seconds of plasma treatment. The last digit corresponds to the amount of time in months or days spent in soil. For example, a sample that is named EV14101 is a sample that has been treated for 10 seconds, placed quarter of an inch from the plasma head, and has spent 1 month in soil. First, we wanted to confirm any changes in the bulk properties of these films because we never wanted any changes in the bulk properties of these films, because changing bulk properties would also result in changing how it degrades, such as the mechanism, and also it could mean changes in its mechanical properties. We did thermal analysis using a DSC, which shows the melting transitions in this figure 3b, and table 2 along with figure 3b shows no change in the melting point of the films even after treatment and even after they were placed in soil. Another thing that confirmed no change in bulk properties was the average molecular weight determined using a GPC or gel permeation chromatography. As we can see, the average molecular weight revolves around 50,000, which means we are not changing any bulk properties of these films. Now that we have established that we are not changing the bulk characteristics of these films, we needed to confirm the changes we are making on the surface. Two good ways of doing it is contact angle and X-ray photon spectroscopy, or XPS measurements. Contact angle measures the angle of a water droplet on the surface, and it is an extremely popular and good method to determine the hydrophilicity or the affinity towards water of the surface. XPS, on the other hand, is a commonly used technique to determine the species or the elements on the surface. Figure 4a and 4b represent the contact angle on an untreated and a treated film. As we can see, the contact angle reduces from 95 degrees to 54 degrees, meaning the surface is getting more hydrophilic, or its affinity towards water is increasing rapidly. Figure 4c corresponds to the contact angle and oxygen containing species as plotted against plasma treatment time. As we can see, as the plasma treatment time increases from 10 to 20 seconds, the contact angle drastically drops from 95 to 54 degrees and hovers around that number. On the other hand, the percentage of oxygen containing species on the surface, as measured by the XPS spectra that I'll talk about in the next slide, increases from 0% to 20% after 10 seconds of treatment, and goes up to 30% and 26% after 15 to 20 seconds of treatment. Now I would like to talk a bit more about the XPS, or X-ray photoelectron spectroscopy spectras a bit more. Figure 5, A and B shows XPS spectra of an untreated and a treated sample. The region corresponding to 286 electron volts on the x-axis represents the amount of oxygen containing groups on the surface. As we can see on the untreated sample, there is no peak observed at 286 electron volts, whereas we can see a giant peak at 286 electron volts for a treated sample. Previously, authors or researchers have shown that plasma treatment suffer from something called as hydrophobic recovery, which means the plasma treatment tend to wear off after being exposed to the atmosphere. So we tested that to see if our films suffered from the same. This was done by plasma treating these samples for 10 and 20 seconds and measuring the contact angle over a period of 1 month. As we can see, the black dotted line represents the contact angle for a untreated sample, which remained constant at about 95 degrees, as we talked before. On the other hand, the plasma treated samples, the contact angle went from 54 degrees to about 61 degrees and hovered around the same over time. Even though the surface started to become a bit less hydrophilic, it retained its hydrophilicity over time as compared to a untreated sample. This is something that we want because we are planning to pre-treat these samples before we actually send them to the farmers. Pre-treatment is a good way of doing the plasma treatment, as it would simplify a lot of things on the end of the farmers. Now let's start to talk about the degradation characteristics of these films and how these films perform in the soil and compost. Figure 7 shows six SEM images of the films, which is a good way of determining the surface morphology of the films. The top 3 pictures show 1, 2, and 3 months of a untreated sample, and the bottom 3 images represent 1, 2, and 3 months of a treated sample. As we can see, as the time progresses, the untreated sample do not undergo any significant amount of degradation on the surface, whereas there is an appreciable amount of degradation happening even after 2 months in soil for the treated samples, as can be observed by the cracks and tears on the surface. It was observed that it took about 2 months to see some appreciable change, and that's why, in order to fast forward the process and select a plasma treatment suitable for our needs, we decided to do a composting trial. Harshal already talked about how we did the compost. I would just do a small recap about it. We did an aerated compost pile with coffee chaff and coffee grounds and soil. The temperatures in the compost were reported to be 5 to 10 degrees higher than the ambient, and triplicates of the samples were placed inside mesh bags in the soil. Samples were taken out after every 15 days to observe under the SEM and run other tests. Figure 9 shows a zoomed out view of samples that have spent 65 days in the compost. The extreme left image shows an untreated EcoVio sample, and it can be seen that there's a bit of soil and microbe on the surface, but other than that, there's no significant degradation that can be observed on the surface. whereas the next two images show appreciable wear and tear or appreciable degradation on the surface. The 20-second plasma treated samples show large tears and cracks on the surface that measures about 200 to 300 microns. This data is supported by carbon dioxide evolution test, which is a commonly used technique to measure the rate and extent of degradation in literature. It measures the amount of CO2 released during the process of degradation of these films. As we can see, the red line represents the CO2 evolution curve for an untreated sample. The green and the black line represents CO2 evolution for treated samples for 10 and 20 seconds respectively. The CO2 evolution test was carried out for 130 days, and the red line or the untreated sample doesn't evolve any CO2 up to 56 days, which is nearly 2 months, which means this process of degradation doesn't start until month 2. This is called the lag phase of degradation, and the entire reason we wanted to plasma treat these samples is to reduce this lag phase that we observe here. In contrast, the plasma treated sample start to degrade and release CO2 after 14 to 21 days in soil. Even though the 10-second treated sample of 1410 flatlines after that, meaning which we hypothesize or which we conclude that the plasma treated region of the film actually degraded away, and thus why the flatlining occurred then. On the other hand, the 20-second plasma treated sample is doing pretty well and shows better signs of degradation. This, combined with the SEM images, proves the hypothesis that plasma treatment is actually accelerating the process of degradation for these films. Finally, I would like to talk about the next steps that we would like to take in terms of plasma treatment and proving our hypothesis. First, we would like to set up an anaerobic biodegradation process to see how these films would perform in the lack of oxygen. Second, we would like to weather these films because when the films are laid out in the fields, it is exposed to rain, sunlight, snow, etc. And it would be nice to see how plasma treatment affects the degradation characteristics of these weathered films. Finally, which is also the final goal of the entire project, we would like to scale up the plasma treatment process and treat larger rolls of films to do on-field trials. All three of them are under progress, and it would be exciting to see how these turn out. Finally, I would like to thank everyone who talked or presented in this webinar, and I would like to thank everyone for giving me a chance to speak and present our research. I'm super excited to see what would happen next in this project, and I would like to wish good luck to all the people who are involved in the project. Anyways, feel free to contact me or Dr. Lewis if you have any questions regarding our research, or feel free to contact Dr. Diaz or Harshil or anyone else involved in the project if you have any other questions. Thank you for listening to me, and have a good one.
All right. Can you hear me?
Yep.
All right. Any questions? And we have actually Professor Lewis here with us, SWAPNIS advisor that can address some of those questions. So please raise your hand or type it in the chat. I'm following the chat here. I don't see new questions. Go ahead, Elizabeth.
Sure. So the plasma treatment, would that be something that would be done before the plastic ever goes out in the field? Like it would come on a roll already treated?
Hi, Elizabeth. This is Chris. Yeah, absolutely. The hydrophobic recovery results that Swapnil presented suggest that at least for 30 days, perhaps longer, that the surface of treatment remains relatively effective. That was an important finding because I think without that, it would necessitate a treatment much closer to the time of installation. So at least as far as we can see right now, we can treat up to 30 days before it would be laid on the field.
Great.
Yeah,
And then,
and Elizabeth, I think you will agree that to ask the growers to bring this like high voltage, dangerous equipment and then try to pass it around is probably not a
no, that's not working.
Bad idea.
it's not a good idea. Yeah.
And then the CO2 coming off of it, is that the chart that had the CO2 coming off of the plastic and showing like degradation over time, was that saying that just like the plastic starts to fall apart after 2 months, or that it just like it's still more or less intact looking as plastic, it's just had a physical change, but it's not like full holes?
So, yeah, that's a good question. The way that we view this is that the degradation is primarily occurring at the surface level as opposed to occurring throughout the bulk. So it wasn't presented here, but we've also, through the course of our degradation experiments, measured things like the molecular weight of the polymer. And we found that the molecular weight of the polymer doesn't appreciably change in spite of the fact that we see this evolution of CO2 and the degradation as observed by the SEM images that he showed. That leads us to conclude that it's primarily a surface phenomena, and sort of like peeling the layers back of an onion. We're degrading the surface, it's degrading away, and then continuing to do so as it progresses through the bulk.
Okay, awesome. That's exciting.
Yeah, and I think again that reduction of the onset of degradation, they're able to tweak that lag phase is also very exciting.
Yeah.
All right, everybody, and I think we're already 5 minutes past the time. Please check out our website. And any last minute questions? I think this is a good time, and if not, thanks very much for joining us here today, and for spending this time catching up on this exciting project. Thank you, and have a good night.